solar receiver for a 60 meter square Scheffler dish. So the outline of the presentation is as follows. First, I'll give a brief overview of what parabolic dish television systems are and what are its drawbacks, followed by how those drawbacks could be overcome by a system called as Scheffler dish system, followed by the parameters which we have analyzed for the receiver designing for this Scheffler dish system, and the experimental setup which we made for testing receiver efficiency. And finally, I'll show a methodology of using quartz glass so that we can improve the thermal efficiency of the receiver. So, briefly, if I have to explain, imagine a 3D paraboloid and imagine the vertex of that paraboloid. Now, if we arrange very small mirrors, say hundreds of mirrors in a parabolic shape, it gives you a parabolic dish. Any incoming solar radiation on this parabolic dish gets reflected and it is concentrated at its focus. At that focus, we put a power conversion unit, which is generally a Stirling engine, which absorbs this high concentration flux and converts this into electrical energy. Now, literature suggests that a lot of R&D has gone in the last few decades, and we have achieved an efficiency of as high as 32%. And yet, it's not very easily visible in as far as implementation of dish Stirling system is concerned. Basically, two reasons are for that, and that the first is the high initial cost, but most importantly, reliability. So, what is this issue which hampers the reliability of these systems? So, the first and foremost thing is the tracking mechanism which the parabolic dish Stirling system incorporates. So, it has to track the sun from morning to evening throughout all the seasons, and the receiver is attached to the dish focus. As a result of which, the the receiver also changes its orientation continuously. Now, because of this continuous change in orientation, it undergoes many issues such as dynamic imbalance, leakages, lubrication issues, etc. As a result of which, they have reliability question marks. So, can we overcome these issues? We can by fixing the position and orientation of the receiver, and to do that, we'll have to switch to Scheffler dish concentrator system. So in the figure you can see the Scheffler dish concentrator system, and it employs an upward facing fixed receiver. The geometry of this parabolic dish is different than the which you saw in the previous slide, because it is not made from the vertex of the paraboloid, but rather it is made by cutting the lateral section of the paraboloid, and the dish performs dual axis tracking about the polar axis of the earth, and as a result of which the receiver remains at a fixed position. The Scheffler dish which we have used for our experimentation is shown over here. The dimensions of the major and minor axis are 10.34 meter and 7.54 meters, and it was made by arranging 770 small mirrors. Now, to help you visualize the size of this Scheffler dish, this image can give you that illustration. So this is one of our cleaning staff performing the routine cleaning operation, and you can just imagine how big the parabolic dish is. So my PhD work was installation of the system of the Scheffler dish, and also designing of the receiver. That was the main part. So there are three parameters that I have analyzed. The first is the opening of the receiver mouth, because we need to make sure that most of the solar radiation that is being reflected, that gets captured by the receiver. Once it is captured at the mouth of the receiver, the next analysis was a receiver shape analysis, that which shape will be the best as far as solar flux heat utilization is concerned, or in other words, which shape gives you the minimum amount of heat loss. And the third one was the fabrication of this receiver through a coil receiver mechanism, and also tested for performance. So the first thing which we did was to analyze that what kind of mouth size you need for the receiver, and for that we have fabricated this system, which you can see over here. It's a square board of 700 mm by 700 mm size, and it consists of three layers. The top layer consists of 25 small mild steel pieces which are connected to K-type thermocouple wires, which comes from the backside. The middle layer is a mineral insulation, and the bottom layer is a ceramic board. Now, mineral insulation and ceramic board make sure that there is no heat loss from the bottom side of the plates. So once we subject this setup to solar flux, you can see this is the flux map at 9:25 a.m. This experimentation was conducted on 26th of November 2021. At 9:25 a.m. this is the flux map. At 12:25 p.m. the flux map rotates, and again at 3:25 p.m. it rotates further. So in these 6 hours, the flux map rotates by 90 degree because of change in sun's position. Now we got the temperature reading from each of these mild steel plates which are connected to a K-type thermocouple, and on the software we were able to replicate that data. Now from this analysis we were able to conclude that we need a 500 mm size of receiver opening. Now once we had the receiver size opening figured out, we conducted analysis on different shapes of the receiver. We did CFD analysis, and we were able to conclude that cone cylindrical shape is the best shape, and hemispherical shape is one of the worst shapes amongst the 6 shapes that we analyzed. Once we concluded that 500 mm opening and cone cylindrical shape is the best one to go ahead with, we fabricated that for a coil receiver, the dimensions of which are shown over here. And then we also insulated it, and we did 3 layers of insulation. So the first innermost layer was inner cladding of mild steel of 2 mm thickness, then a mineral insulation, and outer layer was an aluminium cladding. Then we installed this receiver on a tripod structure, as you can see over here, and it was tilted at an angle which is equal to the local latitude. And then we also had 4 thermowells for recording the temperatures of the heat transfer fluid circulating through it. So now this is the process indication diagram for the thermocoil circuit or our experimental setup. It consists of a solar receiver. Then it goes to the heat exchanger. Then it goes to the expansion tank, followed by to a pump, and then it is again circulated back to the solar receiver. Now initially, when the solar receiver is subjected to solar heat flux, we don't want any heat to be extracted out of the system until unless we reach a stagnation temperature, and therefore we use a bypass line initially. Once we reach that kind of temperature which we need, then we stop the bypass line, and we make sure that the heat transfer fluid goes to the heat exchanger. So this is the actual experimental setup which you can see over here. So as I mentioned earlier, the fluid will go from the receiver to the heat exchanger, which is at point 2, then it goes to the expansion tank, then it comes back, it goes to the pump, and then again recirculated to the receiver. So when the receiver is subjected to solar flux, this is how it looks. It's very bright, and therefore we really can't see anything. So what we did was to use a welding glass. We put that welding glass in front of the camera, and then you can clearly see the kind of flux distribution in the inside the receiver. These were the readings taken for a day of experiment, and we were able to get a stagnation temperature of 230 degrees centigrade, and we were able to extract 13 kilowatt of heat from the system. The thermal efficiency for this particular heat extraction was 55%. But that's still, we knew that there is still scope for improvement, and therefore to make that improvement, what we did was to cover the mouth of the receiver with a quartz glass. So you can see over here that we have put a quartz glass. It has a transmissivity of 93%. What it does is that it will not allow a hot air to come out very easily, and since the hot air is not coming out of the receiver, there will be very minimal amount of convective heat loss, thereby improving the thermal efficiency. So for this configuration, we got the stagnation temperature of 260 degrees centigrade to 265 degrees centigrade. That meant an improvement of almost 35 degrees centigrade. Heat extraction increased by 3 to 6 kilowatt, and thermal efficiency increased by 11 percentage point, that is to 66%. So the solar to electric efficiency for a 66% thermal efficiency system came out to 19%. This is just a theoretical analysis. The overall efficiency calculation part for a 30% assumed efficiency of Stirling engine. So to conclude, we saw that a parabolic discharging system have very good solar to electric efficiency, and they have their own set of drawbacks. So Scheffler dish can overcome these problems because they use a fixed position, fixed orientation receiver. We conducted flux map testing and CFD analysis to figure out the best possible aperture size and the shape. And we conducted analysis using therminal 55 as the heat transfer fluid and achieved the efficiency of thermal efficiency of 66% with a quartz glass cover. And the expected solar to electric efficiency is 19%. Thank you.